The solar system ends somewhere. That much feels obvious. You learn the planets in order. You picture the sun at the center, and somewhere at the outer edge of all of it, there is a boundary, a line, a place where our solar system stops and the rest of the universe begins. Most people put that line somewhere around Pluto. Some put it at Neptune, since Pluto lost its planet status, and Neptune is the last real world out there. Either way, the picture is the same. 8 planets, a few belts of debris, and then nothing. Just empty, cold interstellar space stretching away in every direction forever. That picture is wrong, not slightly wrong, not off by a margin of error. Completely, fundamentally wrong in a way that changes what the solar system actually is. Here is what makes this strange. The confidence is not irrational. Every diagram ever printed in a textbook puts the edge near the planets. Every model hanging in a classroom stops at Neptune or Pluto. The image of a tidy, bounded solar system has been reinforced so consistently and for so long that it feels like established fact. It is not a guess. It feels like something we measured. And in a narrow sense, we did measure the distances to the planets. Those numbers are accurate. Neptune really is about 30 times farther from the Sun than Earth is. Pluto really does orbit out at around 40 times that distance. These are not fabrications. The problem is not the numbers. The problem is the assumption that the planets mark the edge of anything meaningful. They do not. The planets are the innermost portion of the solar system. Everything we think of as our cosmic neighborhood, every world ever visited by a spacecraft, every object ever photographed up close, occupies only a tiny fraction of the Sun's true gravitational reach. Beyond Neptune, beyond Pluto, beyond the scattered field of icy debris that extends past Pluto's orbit, there is more, far more. So much more that describing it in the usual terms almost fails to communicate the reality. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Picture a city. You know the downtown well. You know the streets, the neighborhoods, the boundaries of the city limits. Now imagine being told that the city actually extends hundreds of miles beyond what you thought were its borders, into territory you have never visited, never seen on a map, and never heard named. The downtown you knew is real. The neighborhoods are real. But you were looking at a tiny corner of the full picture and calling it the whole thing. That is roughly the situation with the solar system and what lies beyond the planets. The reason most people have never heard the full version is partly historical and partly practical. For most of the history of astronomy, telescopes could not see far enough. The outer planets were the limit of direct observation. So the outer planets became the limit of the mental model. What could not be seen was not discussed in textbooks written for students. Later, when evidence emerged for something much larger, the textbooks did not catch up. The classroom picture stayed frozen while science moved on. What science moved on to is something enormous. A structure so large that the numbers describing it require a different unit of measurement than the one used for planetary distances. Something that surrounds the entire solar system in every direction, not as a flat disk but as a full sphere. Something containing potentially trillions of objects, preserved unchanged since the solar system formed. so distant from the sun that light itself takes over a year to cross from the sun to its outer boundary. Something that has been sitting there for billions of years, occasionally sending a fragment falling inward toward the sun. A fragment that, when it finally arrives, glows with a tail and crosses the sky above us, and we call it a comet, and we watch it, and almost none of us think about where it came from. That structure has a name, and the fact that most people have never heard it is one of the more remarkable gaps between what science knows and what the rest of us were taught. The solar system does not end anywhere near where you think it does. Most people, if you ask them where the solar system ends, will say something about Pluto. Some will say Neptune. A few will mention the asteroid belt, that ring of rocky debris sitting between Mars and Jupiter, as though it marks some kind of dividing line between the known and the unknown. These answers are not wrong exactly. They are just describing something much smaller than the actual solar system, the way you might describe a country by only naming its capital city. Start with the asteroid belt, because it is the first boundary people reach for. The asteroid belt sits roughly 2.2 to 3.2 astronomical units from the Sun. 1 AU, remember, is the distance from Earth to the Sun, about 93 million miles. The asteroid belt is not a wall, it is not even particularly dense. The total mass of everything in it, every rock and chunk of metal and loose rubble, adds up to roughly 4% of the Moon. Spacecraft have crossed it multiple times without incident. It is a region, not a barrier. Nothing about it signals the end of anything. It is, by any reasonable measure, still very much inside the solar system's inner neighborhood. Then there is Neptune, the 8th planet, the last planet. At roughly 30 AU from the Sun, Neptune sits so far out that sunlight takes more than 4 hours to reach it. It is the boundary that makes intuitive sense, the last of the giant worlds, the outermost of the planets. For a long time, Neptune felt like the frontier. Beyond it was just darkness. But the planets were never the edge of the solar system. They are just the visible part, the part that caught the light and grew large enough to see. The solar system has always extended well past the last planet. We just had not fully worked out how far. Pluto complicated this. Discovered in 1930 and classified as a planet for 76 years, Pluto seemed to push the boundary outward to about 40 AU at its closest approach to the Sun, and nearly 50 AU at its farthest. For decades, Pluto was the edge by default, the last world, the lonely outpost. Then astronomers started finding other objects beyond Neptune's orbit. Hundreds of them, then thousands. Pluto was not the last planet. It was one of the first known members of an entirely different region, the Kuiper Belt, a disc-shaped zone of icy bodies stretching from roughly 30 AU out to about 50 AU, sitting flat against the plane of the solar system, populated with objects that never quite managed to become planets. Pluto is a Kuiper Belt object, one of the larger ones, but not exceptional among its actual neighbours. The discovery of the Kuiper Belt pushed a recognized boundary of the solar system outward again, but it still was not the end. Beyond the Kuiper Belt, the sun keeps blowing. This is not a metaphor. The sun constantly releases a stream of charged particles, electrons, protons, the raw output of its nuclear furnace, in every direction at once. This is the solar wind. It travels outward at hundreds of miles per second, filling an enormous bubble of space with solar material. Inside this bubble, the sun's output physically dominates. Outside it, interstellar space takes over. The boundary between these two regions is called the heliopause. It sits somewhere around 120 AU from the Sun, though the exact distance varies with the Sun's activity cycle and the pressure of the interstellar medium pushing back against it. The heliopause became the boundary that serious astronomers pointed to. It had something the others lacked: a physical mechanism, an actual transition from one regime to another. Inside the heliopause, you are inside the heliosphere, the domain of the Sun's outward breath. Outside, you are technically in interstellar space. Headlines ran with it. The solar system, many people read, had been officially exited. But here is where that framing quietly falls apart. Voyager 1 crossed the heliopause. It did not escape the Sun's gravity, not even close. The solar wind stops. Gravity does not stop. These are two entirely different things, and conflating them is where most popular descriptions of the solar system's edge go wrong. The Sun's gravitational influence, its actual reach, the domain where its gravity is stronger than competing forces, extends incomparably further than the heliopause. The wind is a feature of the Sun's current activity. Gravity is a feature of its mass, and mass does not stop at 120 AU. Mass reaches outward for tens of thousands of AU. Objects that far out are still gravitationally bound to the Sun. They still orbit it. They are still, in every meaningful physical sense, part of the solar system. Think about what that means. Voyager 1 has now travelled for nearly 50 years and reached about 160 AU. It crossed what many people call the boundary of the solar system, and it has barely left. It is still deep inside the Sun's gravitational domain. The actual outer limit of the Sun's gravitational influence is not 120 AU. It is not 160 AU. It is not even close to those numbers. It is somewhere between 100,000 and 200,000 AU out, where the galaxy's own tidal forces begin to overpower the Sun's grip. That is a very different number. That is a number that changes everything about how you picture the solar system's size. Everything inside that gravitational boundary, every object still orbiting the Sun, still bound to it, still falling through space in paths the Sun controls, belongs to the solar system. And stretching through that enormous volume, surrounding the known planets the way an ocean surrounds a tiny island, is a structure that most people have never heard of. The heliopause was never the edge. Neptune was never the edge. Pluto was never the edge. Beyond all of it, past every line we had learned to name as a boundary, there was something else entirely. In 1950, a Dutch astronomer named Jan Oort sat down with the orbital data of 19 known comets and noticed something that did not fit. This was not a glamorous moment in science. There were no major telescopes pointed at some distant mystery, no signal coming in from deep space. Oort was doing what astronomers of that era often did, working through numbers on paper, tracing the mathematics of known objects backward through time, trying to understand where they had originally come from before the Sun's gravity bent their paths inward. It was patient, methodical work, the kind of work that rarely produces anything dramatic. This time, it did. Long-period comets are different from the short-period kind. Short-period comets, like Halley's, return every few decades on predictable schedules. Long-period comets are stranger. They arrive from unexpected directions, swing around the Sun in enormous arcs, and then vanish back into the dark on orbits that take thousands or millions of years to complete. Some appear to be visiting the inner solar system for the first time. Their paths are extreme, stretched so far out that the far end of the orbit sits at distances that made no sense against the known boundaries of the solar system at the time. Oort was not the first person to wonder about this. In 1932, an Estonian astronomer named Ernst Öpik had suggested that long-period comets might originate from a distant reservoir of icy objects surrounding the solar system. The idea was reasonable. Öpik sketched it out, gestured at the possibility, and moved on. He did not build the mathematical case. He did not commit to specific distances or a specific structure. The suggestion sat there unfinished. Oort picked it up and finished it. What he did was deceptively simple. He took the known orbits of 19 long-period comets and worked backward. Before a comet arrives near the sun's gravity has already begun pulling on it, accelerating it, warping its path. To find where a comet actually came from, you have to reverse that process, account for the gravitational influence, and trace the orbit back to its original shape, before the sun started reshaping it. Oort did this for all 19. He calculated what each comet's orbit looked like before it ever entered the inner solar system. The results stopped him. Every single orbit, traced back to its origin point, converged on the same general region of space. Not the same precise point. These were 19 different comets arriving from different directions on different trajectories, but the distances were strikingly consistent. The far ends of their original orbits clustered around a shell somewhere between 20,000 and 100,000 astronomical units from the Sun. That is not a number that has any obvious meaning to the human mind. But consider this. Neptune, the most distant planet, sits at roughly 30 AUO. Pluto averages around 40. The region Oort was pointing to sat 500 to 2,500 times further out than Neptune. It was somewhere no astronomer had seriously imagined looking. No single comet told the story. That is the part worth holding on to. One comet coming from a very distant orbit could have been a coincidence, an oddity, an anomaly. Two could have been dismissed. 19, all pointing to the same distant region, was a pattern, and patterns in astronomy are the closest thing to proof that inference can offer when direct observation is impossible. Oort published his findings in 1950, and his conclusion was bold. He proposed that the solar system is surrounded by an enormous spherical cloud of icy bodies, a reservoir of material extending to extraordinary distances in every direction. Not a disk, not a ring, a sphere, wrapping around the entire solar system from all sides, dense enough to contain billions or trillions of small icy objects, but so remote and so dim that none of it had ever been seen. Comets in this picture were not random wanderers from interstellar space. They were objects knocked loose from this cloud by some external disturbance, sent falling inward on their long arcing paths toward the sun. The proposal was striking for what it required you to accept. Oort was asking the scientific community to believe in a structure of almost incomprehensible scale that no telescope had ever detected, based on the orbital histories of 19 objects. There was no image, there was no direct detection, there was only the mathematics of those 19 paths, converging on a region of space so distant it had never appeared in any observation ever made. Astronomers accepted it anyway, not immediately, and not without skepticism, but the logic was difficult to escape. If the cloud was not there, where were the comets coming from? Their orbits demanded an explanation. Oort had provided one, and no competing explanation held up under the same scrutiny. The math was clean, the pattern was real, and the cloud, whatever it looked like in detail, had to be out there. Oort spent the rest of his career as one of the most respected astronomers of the 20th century. He mapped the rotation of the Milky Way. He contributed foundational work to radio astronomy. He was, by any measure, a scientist of remarkable range. But the thing that carries his name into every conversation about the solar system's outer edge is those 19 comets and the afternoon he spent tracing their origins backward through space. He had never seen a single object in the cloud he had just described, and he never would. The first number you need is 1 astronomical unit, which is the average distance from the Earth to the Sun. That distance is 93 million miles. Written out, it looks like this: 93 million. It is a number large enough that most people cannot hold it in their heads in any meaningful way. The fastest passenger jet ever built would take roughly 20 years to cover it. Light, travelling at 186,000 miles per second, needs just over 8 minutes. 1 astronomical unit. Earth to Sun, that is the baseline. Now build from there. Mars sits about 1.5 AUU out. Jupiter, the largest planet in the solar system, orbits at roughly 5 AUU. Saturn, with its rings, is at about 9.5 AUU. Uranus is around 19 AU. Neptune, the outermost planet, orbits at roughly 30 AU from the Sun. That is 30 times the Earth to Sun distance, about 2.8 billion miles. The Voyager probes took decades to get there, and they were moving fast. Beyond Neptune, Pluto averages around 40 AU along its elliptical path. The Kuiper Belt, the disk of icy debris that is home to Pluto and hundreds of similar worlds, extends out to maybe 50 AUA. In school diagrams, this is where the solar system usually stops. The picture ends around Pluto, sometimes around the Kuiper Belt, and the rest is labelled interstellar space. Here is where that picture falls apart completely. The inner edge of the Oort Cloud begins somewhere around 2000 AU from the Sun. Not 50, not 100, 2000. That is 40 times further from the Sun than Pluto. It is 40 times farther than the edge of everything shown in nearly every diagram of the solar system ever printed. And that is the inner edge, the near side, the closest point where the Oort Cloud even begins. The outer edge of the cloud extends somewhere between 100,000 and 200,000 AU out, 100,000 astronomical units. At the upper end of estimates, nearly 200,000 times the distance from here to the Sun. The numbers have stopped making intuitive sense. That is expected. The human brain evolved to estimate distances measured in feet and miles, maybe across a continent if pressed. It did not evolve to reason about 18 trillion miles without some kind of anchor. So here is an anchor. Imagine the Sun reduced to a marble, a small glass marble, roughly half an inch across, sitting on a table in front of you. On that same scale, Earth would be a grain of sand, tiny, barely visible, and that grain of sand would be sitting about 30 feet from the marble. That is the Earth-Sun distance at this scale, 30 feet. Now find Neptune on this model. That grain of sand representing Neptune sits about 900 feet from the marble Sun, almost 3 football fields away. Pluto is even farther, somewhere around 1,100 feet out. The Kuiper Belt ends at a little over a quarter of a mile from your marble. Now find the inner edge of the Oort Cloud. On this same scale, you would need to travel roughly 60 miles from the marble to reach it. 60 miles. Not feet, not yards, miles. The outer edge of the Oort Cloud at 100,000 AU sits approximately 3,000 miles away from the marble on your table. If you placed that marble in New York City, the outer Oort Cloud would extend past Los Angeles in one direction and deep into the Atlantic Ocean in another. It would be a sphere with a radius of 3,000 miles, surrounding the marble from all directions. And the marble is the sun, and the planets, all of them, Mercury through Neptune, everything we have ever sent a spacecraft to, everything we have ever named and mapped and studied, all of it fits inside a circle smaller than a mile in radius around that marble. The solar system that fills every textbook, every classroom poster, every NASA mission ever flown, occupies a tiny dot at the center of something almost unimaginably larger. Think about light for a moment. Light crosses the Earth-Sun distance in about 8 minutes. It reaches Neptune in roughly 4 hours. Pluto in about 5.5 hours. Light is not slow. It is the fastest thing in the universe. And yet light leaving the sun right now, traveling outward at 186,000 miles every second without pause, will not reach the outer edge of the Oort Cloud for more than a year. Some estimates push that to a year and a half. The sun's own light takes longer to cross its gravitational domain than it takes Earth to complete one full orbit of the sun. That is the actual size of our solar system. And here is the fact that lands hardest of all. Everything inside the Kuiper Belt, the sun, all 8 planets, all the moons, all the asteroids, all the spacecraft we have ever launched, occupies only the innermost fraction of the sun's full gravitational reach, roughly 0.05% of the distance to the outer Oort Cloud, not 5%, not even 1%, 0.05%. The planets are not the solar system. They are a small cluster of objects near the center of the solar system, the way a campfire is not the forest but just a bright point inside one. The Oort Cloud is not a thin shell at the edge of things. It is the bulk of the solar system by volume. It dwarfs everything inside it by a factor that the numbers struggle to express. If the solar system were an ocean, the planets would be the shallow water near the shore. The Oort Cloud would be everything else, all the open water, most of the depth, virtually all of the extent. This is what Jan Oort described from 19 comet orbits in 1950, working with paper calculations and basic telescopic data. He looked at the echoes and inferred the source. A cloud so vast that the planets are a footnote inside it. A cloud so enormous that the light travelling outward from its centre takes over a year just to arrive. At those distances, the word solar system stops meaning what you thought it meant. The Oort Cloud is not one uniform thing. Most illustrations show it as a single fuzzy sphere wrapped around the solar system, a smooth shell of debris sitting at some enormous distance from the sun. That picture is not wrong exactly, but it is incomplete. The actual structure divides into 2 distinct regions, and the difference between them matters more than it might first seem. They behave differently, they respond to different forces, and their relationship to each other is what keeps the whole system functioning the way it does. The inner region has a name most people have never heard. Astronomers call it the Hills Cloud, after the researcher Jack Hills who characterized it in detail in 1981. It begins somewhere around 2000 AU from the Sun and extends outward to perhaps 20,000 AU. That range alone is staggering. Remember that Neptune sits at about 30 AU and Pluto averages roughly 40 AU. The Hills cloud begins where the outer solar system already feels impossibly remote, and it stretches from there across a distance 20 times larger than anything we have ever sent a spacecraft near. But the crucial thing about the Hills cloud is its shape. It is not a sphere, it is a disk, roughly flattened into the same plane that the planets orbit in, the same ecliptic that has organized the solar system since it formed. This is not a coincidence. The inner cloud still feels the gravitational influence of the giant planets. Jupiter and Saturn, even at those distances, exert enough pull to keep the cloud's inner population organized along a preferred plane rather than scattered in all directions. The Hills cloud is also denser than what lies beyond it. The objects are more tightly grouped, relatively speaking, and the region holds a larger concentration of material than the outer cloud per unit of volume. It is, in a sense, the compressed inner layer of a much larger structure. Think of it like sediment at the bottom of a very deep ocean. More material, more structure, organized by the forces acting nearby. Less dramatic from a distance than what lies further out, but more substantial when examined up close. Then there is the outer cloud. This is the structure most people mean when they say the Oort Cloud, and this is where the real strangeness begins. The outer cloud starts somewhere around 20,000 AU and extends to 100,000 AU or further. Unlike the Hills cloud, it is not a disk. It is a full sphere, surrounding the solar system from every direction simultaneously, above and below the ecliptic plane, in every orientation. If you could somehow see it from outside the solar system, it would look like a halo, a vast, dim, spherical shell of frozen debris enclosing everything inside it the way an eggshell encloses its contents. The reason for this difference in shape comes down to forces. The outer cloud is so far from the giant planets that their gravity barely registers at those distances. The force that has shaped the outer cloud over billions of years is not Jupiter, not Saturn, not anything inside the solar system. It is the galaxy. The gravitational tide of the Milky Way, the combined pull of hundreds of billions of stars organized across a disk tens of thousands of light years wide, exerts a differential force on objects at 50,000 or 100,000 AU that has gradually reshuffled their orbital orientations. Over billions of years, this galactic tide has randomized the inclinations of outer cloud objects, tilting their orbits in every direction until the flat disk structure was completely erased and replaced with a sphere. That process is why the outer cloud looks the way it does today. Not an accident, not a coincidence, a consequence of 4.5 billion years of slow gravitational sculpting by the galaxy itself. This spherical shape is also the answer to a question that puzzled early comet observers for a long time. Long-period comets do not arrive from one direction. They do not cluster around the ecliptic plane the way the planets do, the way short-period comets tend to. They arrive from everywhere, from above the plane, from below it, from directions that have no obvious relationship to the flat disk of the solar system at all. The outer cloud is why. When something disturbs an object in the outer cloud, that object can fall inward from any direction, and when it reaches the inner solar system and brightens into a comet, it arrives at an angle that reflects its origin point in a spherical shell, not a flat disk. The sky is isotropic for long-period comets because the reservoir sending them is isotropic. The two regions are not independent of each other. They form a system, and the connection between them is what keeps both regions populated over geological time. The outer cloud, being so loosely bound to the sun, loses objects steadily. Passing stars eject some into interstellar space. The galactic tide strips others away. Every comet that falls inward and gets destroyed or ejected by a planet's gravity is another object permanently removed from the reservoir. If the outer cloud were a closed system with no replenishment, it would have depleted itself long ago. But it is not a closed system. The inner hill's cloud acts as a supply source. Objects from the inner cloud can be perturbed outward into the outer cloud, gradually replenishing the population that the outer cloud is continuously losing. The flow runs inward too, of course, with some inner cloud objects being nudged into trajectories that eventually reach the sun. But the dominant direction of transfer on long timescales is from the inner cloud outward, topping off the outer cloud as the outer cloud drains. This is a remarkably organized system for something sitting at the edge of everything. Two regions, different shapes, different densities, different governing forces, but coupled together and interdependent in a way that has persisted for billions of years. The inner cloud is the reserve, the outer cloud is the frontier, and together they hold something close to the complete outer history of the solar system in frozen form. 4.5 billion years ago, none of this existed. There was no Oort Cloud. There was no outer shell of frozen debris sitting in silence tens of thousands of AU from the sun. There was not even a sun yet, not fully, just a dense collapsing knot of gas and dust spinning faster as it contracted, heating at its core, pulling in more material from the surrounding cloud. Around it, a flat disk of leftover gas and solids began to take shape, the protoplanetary disk, the raw material for everything the solar system would become. The objects now sitting in the Oort Cloud were in there somewhere, part of that disk, nowhere near the outer solar system. They were close in, warm in relative terms, moving fast in tight orbits, slowly clumping together with other material the way small things do when gravity has enough time. This is the part that surprises most people when they first hear it. The Oort Cloud was not built from material that formed out there. The icy bodies now frozen at 20,000 or 50,000 AU from the sun did not form at those distances. They formed much closer, in the same zone that was building planets. The protoplanetary disk was the origin of everything. The planets, the moons, the asteroids, the comets, and the Oort Cloud objects alike. They all started in the same rough neighborhood. What happened next is what separated them. The early solar system was not a calm place. In the first tens of millions of years, the giant planets were growing. Jupiter was the dominant force. It accumulated mass faster than anything else in the disk, pulling in gas and rock and ice at a rate that made it, within a few million years, the largest object orbiting the young sun by an enormous margin. Saturn followed. Together, their gravity transformed the solar system from a relatively orderly disk into something more violent. Objects that passed too close to Jupiter did not simply stay in their original orbits. They got flung. Some fell inward toward the sun and were destroyed. Some hit the early rocky planets, contributing to the bombardment that scarred those surfaces and, in some cases, may have delivered water and organic compounds to the inner planets. Some were ejected outward on hyperbolic trajectories and left the solar system entirely, thrown into interstellar space, never to return. And some were thrown outward, but not quite far enough to escape. These were the ones that mattered for the Oort Cloud. Jupiter and Saturn, and to a lesser extent Uranus and Neptune, scattered smaller objects outward on extremely elliptical orbits. These objects would swing far from the sun, slow down at the outer end of their orbit, and then fall back in again. In those early trajectories, they were vulnerable. If they swung back close enough to a giant planet again, they could be scattered further, or captured, or ejected completely. But the sun's gravity and the gentle influence of passing stars in the sun's birth cluster gradually altered the inner portions of those orbits, lifting what's called the perihelion, the closest approach point, away from the giant planets. Once the perihelion was high enough that Jupiter could no longer reach them, the objects were effectively safe. They settled into wide, slow, stable orbits. They stopped interacting with the inner solar system. They became the Oort Cloud. The bulk of the material that ended up there came from a specific region of the early disk. Models consistently point to the zone between roughly 15 and 35 AU from the Sun, which is the territory where Uranus and Neptune formed. This was cold enough for volatile ices to condense. Water ice, methane, ammonia, carbon monoxide, and the objects that formed there were loaded with these materials. They were also small enough to be moved by the giants rather than to resist them. Objects from closer in tended to hit things or fall into the sun. Objects from this outer range of the disk were in the right place to be launched outward without being destroyed. Most of the frozen bodies now drifting in the Oort Cloud trace their origins to that specific band of the early solar system. The timeline matters here. This process was not slow, not on geological scales. The main phase of Oort Cloud formation happened somewhere between 20 and 50 million years after the solar system began forming. Within the first 50 million years, most of the scattering events that sent objects to their current distant orbits had already happened. That sounds like a long time, but compared to the 4.6 billion years the solar system has existed, it is a brief opening act. By the time the planets had settled into something resembling their current configuration, the Oort Cloud was largely in place. The heavy bombardment continued for a while longer. The inner solar system stayed violent for hundreds of millions of years more, but the distant reservoir was already built. There is something worth sitting with in that timeline. The Oort Cloud is not a product of the mature solar system. It is a product of the young one. It was assembled during the period of maximum chaos, when the giant planets were still migrating, when the disk was still being cleared, when collisions were happening constantly, and the whole system was sorting itself out into something stable. Everything thrown outward in that period, every icy body that survived the scattering without being destroyed or ejected, ended up in those distant orbits where it has sat, essentially untouched, ever since. The deep freeze of space at those distances means there has been no chemistry, no geology, no change. These objects are the same now as they were when they arrived. They are 4.5 billion year old relics of the solar system's most chaotic period, preserved perfectly in the cold. In that sense, the Oort Cloud is a record, not a perfect one, because a lot of material was lost, ejected into interstellar space or destroyed in the early bombardment. But what remains is a snapshot of conditions that no longer exist anywhere else in the solar system. The inner planets have been melted, differentiated, battered, reshaped by volcanism and tectonics. The asteroids have been heated and altered by impacts and solar radiation. The Oort Cloud objects have not. They have been sitting out there since the solar system was young, preserved in the dark, unchanged since Jupiter first flung them outward. Everything that would later arrive in the inner solar system as a comet was already out there, locked into its slow orbit, waiting. If you could somehow reach the Oort Cloud and hold one of its objects, it would not look like much. Most of what lives out there is small, a few kilometers across maybe. Some objects push toward 100 kilometers in diameter, but those are the exceptions. The typical Oort Cloud body is roughly the size of a small city, irregular in shape, dark in color, and covered in a surface that has not been touched by sunlight in any meaningful way for billions of years. It would look, at first glance, like a dirty rock, but look closer and the chemistry tells a different story. These objects are not made of rock in the way Earth is made of rock. They are built from ice. Not just water ice, though that is there too. Methane ice, ethane, ammonia, carbon monoxide frozen solid, hydrogen cyanide locked into the surface. The full list of volatiles reads like a catalogue of the most dangerous chemicals you can imagine, all frozen together into a body smaller than most counties and sitting in darkness at temperatures close to absolute zero. These are the same materials that give comets their brilliant tails when they fall inward toward the sun. When heat finally reaches one of these objects after a long inward journey, it does not melt so much as it erupts. The ices sublimate directly into gas, and that gas carries dust outward into space, and the result is what we see from Earth as a comet's tail. Everything that makes a comet spectacular when it approaches the sun was already sitting there, frozen in the Oort Cloud, waiting. The remarkable thing is how well preserved they are. These objects formed 4.6 billion years ago in the same disk of gas and dust that built the planets, and they have been sitting in deep freeze ever since. Nothing has changed them. No heat, no radiation worth mentioning at those distances, no geological process, no impact large enough to significantly alter their bulk chemistry. They are essentially unchanged samples of the original solar system. The planets have been cooked, compressed, chemically transformed by billions of years of volcanism and bombardment and atmospheric chemistry. The Oort Cloud objects have not. They represent a snapshot of what the raw material of our solar system looked like before any of that happened. Scientists who study comets falling inward from the outer cloud are, in a very real sense, reading the composition of the solar nebula as it existed before the planets existed. Now here is where the picture gets genuinely strange. There are, by most estimates, somewhere between 100 billion and several trillion of these objects out there. The range in those estimates is itself remarkable, and it tells you something important about how little we know. Even pinning down whether the cloud contains 100 billion or 100 trillion objects is beyond current ability. But take the conservative number. Say there are 1 trillion objects larger than a kilometer across. A trillion is 1,000 billion. That is more objects than there are stars in most galaxies. The Oort Cloud, by sheer count of bodies, is one of the most populated regions of the entire solar system. And yet it is, in practice, almost perfectly empty. This is the thing that breaks the intuition. The cloud occupies such an enormous volume of space that even trillions of objects spread across it produce something closer to a hard vacuum than a crowd. The average distance between neighbouring Oort Cloud objects has been estimated at tens of millions of kilometres. To put that in terms that have some grip on the human mind, tens of millions of kilometres is roughly the distance between Earth and Mars at their closest approach. That is the gap between individual objects. Mars, when it is nearest to us, still takes anywhere from 3 to 7 months to reach with current spacecraft, and in the Oort Cloud, that is the typical space between two neighbours. Imagine standing on the surface of one of these objects. You're on a dark, frozen body a few kilometers across. The surface is quiet. There is no atmosphere, no wind, no sound of any kind. You look up. The stars are there, just as sharp and numerous as they would be from anywhere in deep space. And among those stars, you look for the sun. You find it. It does not look like the sun you know. It looks like a bright star. Brilliant, yes, measurably brighter than everything else around it, but a point, not a disk, not a source of warmth you could feel. Just a slightly more intense dot among billions of other dots. You look for neighboring objects in the cloud. You see nothing. Not because there are no neighbors, but because even if one sits tens of millions of kilometers away, it is too small and too dark to resolve with the naked eye against the backdrop of space. This is the thing that illustrations always get wrong. Every diagram, every artist's rendering of the Oort Cloud shows it as a haze of objects, a visible swarm, a cloud in the way the word cloud suggests something you could see. In reality, you could stand inside it and have no idea it existed. The objects are real, the trillions of bodies are real, but the distances between them are so vast that the cloud is, experientially, indistinguishable from empty space. It is the loneliest place in the solar system. Whatever sits out there has been sitting in that isolation since before the Earth had oceans. What you would be holding is one of the oldest unaltered pieces of the early solar system that exists anywhere, and there would be nothing else in sight. The Oort Cloud does not exist in isolation from the rest of the galaxy. That might seem like an obvious statement. Nothing exists in true isolation. But for the Oort Cloud it means something specific and strange. At the distances we are talking about, somewhere between 50,000 and 100,000 astronomical units from the Sun, the Sun's gravitational grip has weakened to something barely distinguishable from nothing. And when the Sun's pull drops that low, something else begins to matter. The Milky Way itself starts pulling back. This is called the galactic tide. Not a tide in the ocean sense, though the physics are related. A tide, in the gravitational sense, is what happens when one massive object pulls differently on 2 points at different distances from it. The Moon pulls slightly harder on the side of Earth facing it than on the side facing away. That difference, that gradient across Earth's diameter, is what raises the oceans. The galactic tide works the same way, just at a scale that is almost impossible to hold in your mind. The Milky Way contains hundreds of billions of stars, enormous amounts of dark matter, vast reservoirs of gas and dust. Its total gravitational influence is staggering, and the Sun, sitting out in one of the galaxy's spiral arms, roughly 26, 000 light years from the galactic center, is not immune to any of it. Here is the key detail. The Sun and its outermost objects are not at the same distance from the galactic center. They cannot be. The Oort Cloud extends outward in every direction. Objects on the side of the cloud closest to the galactic center are slightly closer to it than the Sun is, while objects on the far side are slightly farther. That tiny positional difference translates into a tiny difference in gravitational acceleration. Objects closer to the galactic center are being pulled toward it fractionally harder. Objects farther away are being pulled fractionally less. The Sun sits in the middle, experiencing its own pull. And the result of all these fractional differences, acting continuously over millions and billions of years, is that orbits get twisted, stretched, tilted. Objects that might have been orbiting in the flat plane of the solar system gradually have their orbital inclinations randomized by the galaxy's uneven tug. This is why the outer Oort cloud is a sphere. It is not shaped like a disk, the way the planets are, or even like the slightly flattened inner Hills cloud. It is a full sphere surrounding the solar system in every direction, and the reason for that shape is the galactic tide. Over billions of years, the differential pull of the galaxy has worked on orbital inclinations the way wind works on a pile of leaves, scattering them in every direction, randomizing orientations that might otherwise have stayed flat. The spherical shape of the outer cloud is not an accident of formation. It is the direct signature of galactic gravity written into the structure of our own solar system. What you can do with that realization is significant. When astronomers look at long-period comets arriving from the Oort cloud and notice that they come from every direction in the sky, not concentrated near the plane of the solar system, but distributed across the full celestial sphere, that pattern is direct evidence of the galactic tide at work. The randomized arrival directions of comets are the observable fingerprint of a force operating at galactic scales, sculpting our solar system's outer edge from a distance of tens of thousands of light years. But the galactic tide does not just reshape orbits over long timescales and leave them stable. It keeps working. And for some objects in the outer cloud, the continuous gentle distortion of the galactic tide is enough to tip an orbit across a threshold. An object that has been circling the Sun in a roughly stable path for billions of years can, through the slow accumulation of galactic perturbations, find its orbit stretched just enough that its closest approach to the Sun drops from tens of thousands of AU into the realm of the inner solar system. It does not happen quickly. The process can take millions of years of continuous gravitational nudging before the orbit shifts far enough. But it happens. The galactic tide is one of the primary engines that sends comets falling inward from the Oort cloud. Every long-period comet arriving in the inner solar system likely owes some part of its journey to this force. There is something almost vertiginous about this once you sit with it. The comet you might see crossing the sky over the course of a few weeks, bright enough to see with the naked eye, began its fall because the Milky Way pulled on it, not the Sun, not a passing star, the galaxy. A structure 100,000 light-years across has been exerting a slow and patient influence on objects at the edge of our solar system. Those objects eventually fell inward and became the comets that ancient civilizations watched with terror and that modern astronomers track with spectrographs. The Milky Way reaches all the way into our local experience of the sky. This also means the Oort cloud cannot be understood purely as a solar phenomenon. It is embedded in a galactic context. The shape of the cloud, the stability of individual orbits within it, the rate at which comets are fed into the inner solar system, all of these depend not just on the Sun's gravity, but on the structure and mass distribution of the galaxy around us. Change the position of the solar system within the Milky Way, move it closer to the denser galactic disk or nearer the center, the galactic tide strengthens. The Oort cloud would lose objects faster. Comet delivery to the inner solar system would increase. The solar system's outer edge is not a fixed or self-contained thing. It responds to where the solar system happens to be sitting within the larger structure of the galaxy at any given moment. The galaxy is not just the background against which the solar system sits. It is an active force shaping what the solar system's outer edge looks like. Getting an object from the Oort cloud into the inner solar system is not a quick or simple process. There is no single trigger, no one event that reliably sends an icy body falling inward. Instead, there are three mechanisms, each operating on different timescales, each capable of nudging something out of a stable orbit it has held for billions of years and setting it on a path toward the sun. The galactic tide, which was introduced in the previous section, is the most constant of these forces. It operates on everything in the outer cloud simultaneously, always pulling, always reshaping orbits in subtle ways. Over millions of years, that constant differential pull can accumulate enough to make certain orbits unstable. An object that was perfectly balanced in its distant loop gradually finds its path distorted. The far end of the orbit gets stretched. The near end dips slightly closer to the sun. Eventually, the geometry tips far enough that the object begins a genuine inward fall. This is not dramatic. Nothing explodes. Nothing collides. The object simply reaches a threshold where its orbit no longer keeps it safely in the outer cloud, and it begins a long, slow descent. The second mechanism is a passing star. On average, a star wanders within a few light years of the sun roughly every 50,000 years. That sounds infrequent. Over the full 4.5 billion year history of the solar system, it represents tens of thousands of individual encounters. Each one is a gravitational event. Even a star passing 2 or 3 light years away exerts a measurable pull on Oort Cloud objects, especially those in the outermost, most loosely bound regions of the cloud. The effect is not uniform. Some objects get nudged outward, and if the nudge is strong enough, they escape the sun's gravity entirely and drift away into interstellar space, lost forever. Others get nudged inward just enough that their orbit tips towards the inner solar system. The difference between those two outcomes can be a very small change in velocity. We are talking about a gravitational push, so gentle it would be undetectable over a human lifetime, but enough, over the right geometry, to redirect a comet's entire future. The third mechanism is the least common but potentially the most powerful. Giant molecular clouds are exactly what they sound like, vast regions of dense gas and dust scattered throughout the galaxy, some of them containing millions of times the mass of the sun. The solar system passes through or near these clouds occasionally during its long orbit around the galactic center. When it does, the added gravitational influence can disturb the outer Oort cloud on a massive scale, sending large numbers of objects inward at roughly the same time. Some researchers have linked periodic spikes in the comet impact record on Earth to these encounters. The evidence is not conclusive, but the physics is real. A close passage with a molecular cloud is the Oort cloud equivalent of shaking a snow globe. Now consider what happens after one of these mechanisms does its work. An object gets perturbed, its orbit changes, it begins to fall inward, but it does not arrive quickly. The orbit of a typical Oort cloud object is so enormous that even after being nudged, the journey toward the sun takes an almost incomprehensible amount of time. A comet originating from the outer cloud at say 80,000 AU, falling inward on a highly elliptical orbit, might take several million years just to complete one pass through the inner solar system. Most of that time is spent far from the sun, moving slowly at the outer reaches of the orbit, covering the vast distance at a crawl. The object spends only a tiny fraction of its total orbital period anywhere near the planets. For most of that journey, nothing visible happens. The object is a frozen chunk of ice and rock, dark, silent, and completely indistinguishable from any other piece of debris in space. It carries the same chemical composition it had when it formed 4.5 billion years ago. Water ice, methane, carbon monoxide, ammonia, hydrogen cyanide. None of that has changed. The outer solar system is cold enough to preserve these materials almost indefinitely. The object has been in deep freeze since the early solar system, and the fall inward does not immediately change that. For millions of years of travel, it remains frozen and invisible. Then it crosses a threshold. Somewhere around the orbit of Jupiter, the sun's heat finally begins to matter. At 5 AU, solar radiation is 25 times weaker than it is at Earth. But it is enough. The ices near the surface begin to sublimate, converting directly from solid to gas without passing through liquid form. Gases escape, carrying dust and small particles with them. A cloud of gas and dust begins to form around the nucleus. This is the coma, the fuzzy atmosphere that gives comets their distinctive blurred appearance through a telescope. As the comet continues inward, the solar wind, a constant stream of charged particles flowing out from the sun, pushes the escaping gas and dust away from the nucleus, always away from the sun regardless of the direction of travel. This is the tail, or rather the tails, because most comets develop two, one made of ionized gas pointing directly away from the sun, one made of dust curving gently along the orbital path. A bright naked eye comet, the kind that gets reported in news articles and draws people outside at night to look up, may be visible for a few weeks, sometimes a few months. Then it passes through the inner solar system, rounds the sun, and heads outward again on the far leg of its orbit, fading as the distance grows and the ices stop sublimating. It may not return for millions of years, or it may be captured by a planet's gravity and forced into a shorter orbit, or it may be ejected entirely. The outcome depends on every gravitational encounter it has along the way, and those are effectively impossible to predict with precision. What is certain is the timescale. The mechanics of Oort Cloud perturbation, the long orbital fall, the slow approach, the brief bright passage through the inner solar system, all of it runs on a clock measured in millions of years. By the time a long period comet is bright enough to see with the naked eye from Earth, the journey that sent it here may have begun millions of years ago. The only direct evidence that the Oort cloud exists is the comets it occasionally sends inward. That is worth sitting with for a moment. Astronomers have spent decades building detailed models of this structure, mapping its two regions, calculating its mass, estimating its population in the trillions, describing how galactic tides sculpt its outer shell, and yet not a single object has ever been confirmed to actually reside there. No telescope has resolved an Oort cloud body sitting in its orbit. No spacecraft has flown near one. The entire edifice of what we know about the outer solar system's most enormous feature rests on a specific kind of indirect reasoning. We have never seen the cloud. We have only seen what falls out of it. This is not a small caveat. This is the central fact about the Oort cloud. Everything, the shape, the size, the population estimates, the two-region structure, is inferred. The cloud is, in a very real sense, a conclusion rather than an observation. The comets that reach the inner solar system are the only physical data points we have, and working backward from those comets to the reservoir that produced them is one of the most careful and consequential pieces of detective work in the history of astronomy. Here is how it works. When a long-period comet swings through the inner solar system, astronomers can measure its current trajectory with considerable precision. But the trajectory we observe today has been distorted. As the comet fell inward over millions of years, the gravitational pull of Jupiter, Saturn, and the other giant planets steadily bent its path, nudging it away from whatever original trajectory sent it falling sunward in the first place. To find where the comet actually came from, you'd have to run the physics backward, strip out every gravitational interaction it experienced on the way in, compute the orbit it would have had before any planet touched it. That original orbit, called the original osculating orbit, tells you where the comet was before everything changed. When Jan Oort did this for 19 known comets in 1950, the result was striking. The original orbits did not scatter randomly across space. They clustered. The farthest points of those orbits, the aphelia, the places where each comet had been slowest and most distant before beginning its inward fall, grouped together in a zone somewhere between 20,000 and 150,000 AU from the Sun. Not near any planet, not in the Kuiper Belt, not somewhere close and easy to explain, impossibly far out, in a region that no instrument of that era had any hope of directly examining. And the aphelia came from all directions in the sky, not clustered along the plane of the solar system the way short-period comets are, but distributed across every angle of the celestial sphere. That told Oort the source had to be roughly spherical, not a disk, a shell. 19 comets is not a large sample. Oort knew this. But the pattern was clean enough and the alternative explanations weak enough that the hypothesis held. The cloud had to be there. The modern dataset is far larger. Hundreds of long-period comets have now had their original orbits computed. The pattern Oort found in 19 cases survives intact across all of them. The aphelia distribution remains sharply peaked. Objects cluster between roughly 25,000 and 50,000 AU in numbers that cannot be explained by chance or by any other known mechanism. The statistical signal is overwhelming. Run the numbers with any reasonable assumption about how comets behave, and the same answer comes back every time. There is a vast spherical reservoir out there at those distances, and it is continuously leaking objects inward at roughly the rate we observe. Nothing else fits. That phrase matters. Science rarely deals in certainties, but the Oort cloud sits in a narrow category where the alternative is not uncertainty, but incoherence. If the cloud did not exist, long-period comets could not exist in the numbers and distribution we observe. You cannot get comets arriving from random directions in the sky, on orbits that trace back to 40,000 AUU, without a source at 40,000 AUU. The comets demand the cloud the way a shadow demands an object casting it. This kind of reasoning has worked before. In the 1840s, astronomers noticed that Uranus was not quite following the orbit Newton's laws predicted for it. Something was pulling on it. The perturbations were small but consistent, and two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unseen planet would have to be to produce exactly those deviations. When astronomers pointed a telescope at the predicted location in September of 1846, Neptune was there, almost exactly where the math said it would be. The planet had been found by inference before it was found by observation. The Oort cloud was found the same way, except the confirming observation has never come. We have the inference, we have the math, we have hundreds of comets all pointing at the same answer. What we do not have is the image of a single object sitting in its orbit at 50,000 AU, confirming what the equations say. That gap between inference and direct observation is not a weakness in the science. The math is solid, the comet data is real, and the conclusion is about as secure as conclusions get in astronomy without a direct image. But it does mean the Oort cloud remains in a strange epistemic category. We know it is there the way you can know a room is full of people in the dark, not because you see them, but because you can hear them breathing. Every long-period comet that passes through the inner solar system is a message from the outer edge, and for decades astronomers were reading the messages without quite understanding where they had been sent from. The most famous comet in recorded human history almost certainly did not come from the Oort cloud. Halley's Comet returns every 76 years. Ancient Babylonians recorded it. Chinese astronomers tracked it for centuries. Edmund Halley himself recognized in 1705 that the bright comets of 1531, 1607, 1682 were the same object coming back around. That regularity is exactly the problem. A 76-year orbital period puts Halley firmly in the category of short-period comets, objects that loop through the inner solar system frequently enough to be caught, studied, and predicted. Oort cloud comets don't do that. They arrive on orbits so enormous that a single trip around the Sun takes hundreds of thousands or millions of years. Halley's most likely origin is the Kuiper Belt, the disk of icy bodies just beyond Neptune. Though some astronomers think it may have started as a genuine Oort cloud object, whose orbit was gradually shortened over millions of years by repeated gravitational nudges from the giant planets. Either way, it is not what Oort was describing when he proposed his cloud. Halley is a familiar visitor. True Oort cloud comets are not visitors. They are strangers arriving for the first time. Comet West, which appeared in early 1976, was something different entirely. It became one of the brightest comets of the 20th century, visible to the naked eye even in morning twilight, with a broad fan-shaped tail that observers described as spectacular. When astronomers computed its original orbit, tracing its path backward through the gravitational influence of the planets to reconstruct where it had been before, the numbers were striking. Comet West had an orbital period measured not in years or centuries, but in millions of years. It had almost certainly never passed through the inner solar system before. It came from the deep outer cloud, fell inward on a trajectory that had been undisturbed for billions of years, swung around the Sun and departed again. During its brief pass, it broke into 4 pieces as tidal stresses from the Sun tore it apart. The fragmentation gave astronomers an unexpected look at fresh interior material, chemically pristine ice that had never been exposed to solar radiation before that single approach. Comet West didn't just put on a show. It cracked itself open and let scientists read what was inside. Comet Hale-Bopp is another entry in the genuine Oort cloud column. Discovered in 1995 by 2 amateur astronomers working independently on the same night, it became visible to the naked eye in 1996 and stayed that way until late 1997. 18 months of naked eye visibility. Most comets are spectacular for a few weeks at most. Hale-Bopp held the sky for a year and a half, which tells you something about its size. Estimates put its nucleus at roughly 60 kilometers across, one of the largest cometary nuclei ever measured. Its previous orbital period, calculated from its inbound trajectory, was somewhere around 4,000 years. That means it had visited the inner solar system at least once before in recorded human prehistory. Its outbound trajectory after the 1997 approach was altered by planetary gravity, shortening its future period to around 2,500 years. Hale-Bopp sits in an interesting middle category. not a first-time visitor like Comet West, but far from a short-period comet like Halley. Its chemical composition was studied extensively and found to include water ice, carbon monoxide, dust silicates, a range of organic molecules, essentially a sample of the early outer solar system preserved in deep freeze for billions of years. Then there is Comet Ison, which arrived in 2013 carrying enormous expectations and delivered something more complicated. Discovered in 2012 by two astronomers using a Russian telescope, Ison was immediately recognized as a dynamically new comet, almost certainly making its first pass through the inner solar system after falling inward from the Oort Cloud. Its orbital calculations pointed to an origin at roughly 58,000 AU. First-time visitors tend to arrive with high concentrations of volatile ices on their surfaces because those ices have never been burned off by solar heat before. Ison was predicted to be extraordinarily bright as those fresh ices vaporized. What actually happened was that Ison approached the Sun to within about 1.1 million kilometers on Thanksgiving Day, 2013, and did not survive. The nucleus disintegrated. Ison was destroyed before it could complete its first solar orbit. The remnants scattered and faded. What Ison gave astronomers before it fell apart was still valuable: spectroscopic data on a chemically fresh object that had never been this close to a star before, carrying material unchanged since the early solar system. This is the category that astronomers care most about. Dynamically new comets, objects falling inward for the first time, or very close to the first time. Their surfaces have never been heated, their volatile ices have never outgassed. The chemistry sitting on the outer centimeters of their nuclei is, in a very real sense, original, unchanged since these objects formed 4.6 billion years ago in the disk of gas and dust that built the planets. When a spectroscope is pointed at a dynamically new comet as it begins to warm near the Sun, what comes off the surface is a direct chemical signal from the early solar system. No other object we can study gives us access to that era so cleanly. The bright comets that have defined human history, the ones that triggered superstitions, that were painted into medieval manuscripts, that drove people outside on cold nights to stare upward. Most of the truly dramatic ones, the ones arriving with no prior solar warming, were first-time visitors from the outer cloud. Each one of them is a chunk of the original solar system falling inward for the first, or nearly the first, time in billions of years. Its surface chemistry is a read on conditions that have not existed anywhere else since the planets formed. Before you reach the Oort Cloud, you pass through something else entirely. Between the realm of the planets and the vast frozen shell of the outer solar system, there is a third region that most people have never heard of, and that took astronomers most of the 20th century to properly understand. It is called the Kuiper Belt. It sits just beyond Neptune, beginning at roughly 30 astronomical units from the Sun, and extending outward to somewhere around 50 AU. That puts it in a completely different category from anything the inner solar system contains. Yet compared to what lies beyond it, the Kuiper Belt is practically next door. The Kuiper Belt is a disc-shaped ring of icy debris aligned with the plane of the solar system, populated by objects that never quite managed to become planets. Most of them are small, a few kilometers across, frozen remnants of the same protoplanetary disk that built Neptune and Uranus. But some are not small at all. Pluto is in the Kuiper Belt. So is Eris, which is slightly more massive than Pluto and orbits even farther out, reaching nearly 100 AU at its most distant point. Makemake is in the Kuiper belt. Haumea is in the Kuiper belt. These are dwarf planets, worlds with enough mass to pull themselves into rounded shapes, geologically complex in their own quiet way, sitting in the deep cold beyond the last of the gas giants. Pluto has mountains made of water ice and a thin nitrogen atmosphere that collapses and refreezes as it swings through its orbit. These are not blank rocks. They are places. The Kuiper belt is also where short-period comets come from. When astronomers talk about comets that return every few decades or every few centuries, those objects trace their origins back to this disk. A gravitational nudge from Neptune or one of the other giant planets can knock a Kuiper belt object out of its stable orbit and send it falling inward. The journey from 40 AU to the inner solar system takes thousands of years. But the important distinction is this. Kuiper belt comets come in on flat, well-behaved trajectories aligned with the plane of the solar system. Long-period comets arrive from every direction, from above, from below, from angles that have nothing to do with the ecliptic. That difference in geometry is one of the core pieces of evidence for the Oort Cloud. Something spherical and enormous is feeding those long-period orbits, and the Kuiper belt cannot be that source. So the picture seemed clean for a while. The Kuiper belt handled the short-period comets. The Oort Cloud, somewhere far beyond, handled the long-period ones. Two separate reservoirs, two separate populations, a tidy model. Then, in November of 2003, a small team of astronomers studying distant solar system objects found something that did not fit into either category. They called it Sedna. Sedna is a small reddish world, somewhere around 1,000 kilometers across. Its surface is one of the reddest in the solar system, likely stained by complex organic molecules called tholins. The same chemistry that gives Pluto its rusty patches and that forms wherever ultraviolet radiation hits methane ice over long timescales. It was not Sedna's surface that made astronomers stop cold. It was its orbit. At its closest approach to the Sun, Sedna comes in to roughly 76 AU. That alone puts it well beyond the Kuiper belt, but its orbit is enormously elongated, stretching outward to roughly 900 AU at its farthest point. Its orbital period is approximately 11,400 years. To put that in terms of human time, the last time Sedna was anywhere near its closest approach to the Sun, agriculture had barely been invented. The wheel did not exist. There were no written languages anywhere on Earth. The problem Sedna created was immediate and obvious. It was too far out to be a Kuiper belt object. Nothing in the Kuiper belt reaches 76 AU at its closest approach. The belt simply does not extend that far. But it was also far too close, far too tightly bound to the Sun to be a true Oort Cloud object. The inner edge of the Oort Cloud is generally placed somewhere around 2000 AUA. Sedna's farthest point, at 900 AUA, barely grazes half that distance. It sits in a gap between two known regions, too distant for one and not nearly distant enough for the other. One astronomer described it as finding a city in the middle of the ocean with no bridges and no boats. Several explanations were proposed. Some researchers argued that Sedna represents the first detected member of the inner Oort Cloud, also called the Hills Cloud, the denser, disc-shaped inner region that sits inside the full spherical shell. That would push the inner edge of the Oort Cloud system closer to the Sun than previously assumed. That would be a significant revision. Others argued that Sedna belongs to a third structure entirely, a region sometimes called the extended scattered disk or the detached disk, a population of objects pushed onto highly elongated orbits by gravitational interactions during the early solar system. Neither fully Kuiper Belt nor truly Oort Cloud. The most compelling explanation involves the Sun's birth cluster. When the Sun formed, it was not alone. It was born inside a dense stellar nursery alongside hundreds of other young stars. For its first tens of millions of years, the Sun had neighbours, close ones, close enough to exert real gravitational influence on the material surrounding it. A star passing within a few hundred AU during that early period could have pushed a Kuiper Belt object onto an orbit exactly like Sedna's, stretched far outward, but not far enough to join the true cloud. The birth cluster eventually dispersed, the neighbouring stars scattered across the galaxy. Sedna was left on its strange elongated path, frozen evidence of a time when the Sun was not alone. Since Sedna's discovery, a handful of other objects with similarly strange extended orbits have been found. They are sometimes called sednoids, and each one deepens the puzzle. There may be thousands more out there, too distant and too faint for current telescopes to detect. Sedna is out there right now completing its 11,400-year orbit. Nobody is entirely certain what to call it or what it implies about the region between the Kuiper Belt and the true cloud. The Oort Cloud has neighbours, and its neighbours are not entirely harmless. Most people picture the space around our solar system as fundamentally empty, a vast, quiet dark, with the nearest star sitting 4.2 light-years away like a distant lighthouse. Harmless, stationary. But stars are not stationary. Every star in the galaxy is moving, and from time to time one of them moves close enough to matter. On average, a star passes within a few light-years of the Sun roughly every 50,000 years. That sounds infrequent. Over the 4.6 billion-year history of the solar system, though, it adds up to somewhere in the range of 90,000 such encounters. Tens of thousands of passing stars, each one reaching out gravitationally into the outermost edges of the Oort Cloud, tugging at the loosely bound objects sitting there in the dark. The cumulative effect is staggering. The Oort Cloud, over billions of years, has been continuously jostled, prodded, and reshaped by the stellar traffic moving through our corner of the galaxy. To understand why this matters, you have to remember how weakly the Sun holds its outermost objects. At 50,000 or 100,000 AU, the Sun's gravity is barely a whisper. An object at that distance completes a single orbit over millions of years, drifting along on a path so wide and slow that almost any outside force can perturb it. A passing star does not need to come dangerously close to cause serious disruption. Even a star passing within 1 or 2 light-years exerts a gravitational pull that is enough to slightly alter the trajectories of Oort Cloud objects in its path. Some of those objects get pushed outward, stripped from the solar system entirely, and sent into interstellar space. Others get nudged inward. Their orbits tighten. Over thousands or millions of years, they fall toward the Sun, picking up speed, and eventually they arrive in the inner solar system as long-period comets. A bright comet blazing across the sky might owe its entire journey to a star that passed within a light-year of the Sunday 10 million years ago and gave it the slightest push. There is one particular star that astronomers are watching. Its name is Gliese 710. It is an orange dwarf, about 64% the mass of the Sun, currently sitting roughly 62 light-years away. It is approaching. Models based on precise measurements from the Gaia Space Observatory project that Gliese 710 will pass within about 0.06 light years of the Sun in approximately 1.3 million years. That is roughly 13,000 AU at closest approach, well inside the outer Oort Cloud. This will be the closest known stellar passage in the history of the solar system. At that distance, Gliese 710's gravitational influence on the Oort Cloud will not be subtle. Simulations suggest it could send a significant shower of comets inward, dramatically increasing the number of long-period comets entering the inner solar system over the following millions of years. The Earth will not be threatened directly, but the comet flux arriving in the inner solar system could increase substantially, and some fraction of those comets will cross Earth's orbital path. 1.3 million years from now is not tomorrow, but on astronomical timescales it is close. What makes Gliese 710 especially interesting is not just what it will do, it is what it tells us about what has already happened. If one star we can currently track is going to pass this close, then over the past 4.6 billion years, many other stars must have passed at comparable or even shorter distances, each one sending its own shower of comets inward, reshaping the structure of the cloud in ways that accumulated across deep time. The Oort cloud we see today is not the same cloud that existed 2 billion years ago, or even 500 million years ago. It has been continuously sculpted by encounters we can only estimate and never directly observe. But the most profound stellar influence on the Oort cloud did not come from passing strangers. It came from family. The Sun was not born alone. Stars forming clusters, dense nurseries of gas and dust that collapse and ignite tens or hundreds of new stars in a relatively small region of space. In its first tens of millions of years, the Sun was surrounded by hundreds of sibling stars, all formed from the same parent cloud, all in close proximity. The distances between these birth cluster stars were vastly smaller than the typical distances between stars in the present-day galaxy. They were neighbours in a way that stars almost never are, and that closeness had consequences. As the Oort cloud was forming, as the giant planets were flinging planetesimals outward into distant orbits, those sibling stars were right there. Their gravity was constantly tugging on the outer material. Some objects were perturbed into even wider orbits than the planets alone could have produced. Others were scattered into the spherical distribution that defines the outer cloud. The overall shape of the Oort cloud, the way it wraps around the solar system from all directions rather than lying flat in the plane of the planets, may be partly a product of those early stellar neighbours pushing and pulling from every angle before the cluster dispersed. Within the first 100 million years or so, the birth cluster broke apart. The sibling stars drifted away on their individual orbits through the galaxy, spreading across distances so vast they are now unidentifiable. The Sun has no known siblings, but their influence is still written into the structure of what they left behind. This is what makes the Oort cloud's history so strange to sit with. It formed through chaos, planetary giants throwing material outward, sibling stars disturbing it from outside, the galaxy's own tidal forces bending orbits over billions of years, and then more passing stars, decade by decade, century by century, epoch by epoch, slowly eroding the outer edges while occasionally sending a fragment plunging inward to light up the sky. The cloud is not a static archive, it is a living structure, still responding to forces that have been acting on it since before the Earth existed. There is a star out there right now, 62 light years away, closing the distance at around 51,000 kilometers per hour relative to the Sun. In 1.3 million years it will pass through the outer Oort Cloud. Nobody alive today, and nobody alive for 1,000 generations after today, will witness it, but the comets it sends inward will eventually arrive. The stellar neighborhood has never been as empty or as static as it looks on a clear night. Here is a question that sounds simple and is not. Where does the solar system actually end? Most people have some version of an answer already loaded. Pluto maybe, or Neptune if they remember that Pluto got reclassified. Some have heard of the Kuiper belt and would draw the line somewhere out there, past the last recognizable planet, where the disk of icy debris finally thins out around 50 AU. That feels like an edge. It has the shape of an edge. But none of those answers survive contact with what the solar system actually is, because they are all describing the same small inner zone and mistaking it for the whole thing. So let's take the question seriously. There are several different definitions of where the solar system ends, and they give different answers. Each one is defensible. None of them is clean. The first definition is the one Voyager 1 gave us. In 2012, after 35 years of travel, Voyager 1 crossed a boundary called the heliopause at roughly 121 AU from the Sun. The heliopause is where the solar wind stops. The Sun constantly blows a stream of charged particles outward in every direction, a thin hot wind that pushes against the surrounding interstellar medium. At some point, that outward pressure equals the inward pressure of particles from the rest of the galaxy. That point is the heliopause. Cross it, and you are no longer inside the Sun's wind. You are in interstellar space. By that definition, the solar system ends at around 120 AUW. Voyager 1 is currently past it. It is, by that measure, already outside the solar system. But here is the problem. The solar wind stopping is not the same thing as the Sun's gravity stopping. Gravity does not have a heliopause. It does not run out of push and equalize against some opposing force. It falls off with distance, slowly, but it never reaches zero. And the Sun's gravitational grip on objects extends vastly further than 120 AUW. Pluto at 40 AU is clearly bound to the Sun. Sedna at its farthest point, nearly 900 AU, is still bound to the Sun. Objects in the inner Oort Cloud at 5,000 AU are still bound. Objects in the outer Oort Cloud at 50,000 AU are still bound. Barely. But they are still circling the Sun on orbits that close, eventually, if left undisturbed. This brings you to a second definition. Astronomers call it the Hill sphere, the region around an object where its gravity dominates over competing gravitational influences. For the Sun, the competing influence at large distances is the Milky Way galaxy itself. The galactic tide, as discussed, is not a negligible force at 50,000 or 100,000 AU. The galaxy is pulling on those outermost objects with a force that begins to rival the Sun's own pull. The point at which the galaxy wins is roughly where the outer Oort Cloud ends. Estimates vary, but the Hill sphere of the Sun sits somewhere between 100,000 and 200,000 AU. By this definition, the solar system ends at the outer edge of the Oort Cloud. Everything inside is Sun territory. Everything beyond is galactic territory. That sounds like a clean answer. It is not. The objects at the outer edge of the Oort Cloud are barely hanging on. Their orbits are so weakly bound to the Sun that an encounter with a passing star or a sustained pull from the galactic tide can sever the connection entirely. They are not stably orbiting in any robust sense. They are drifting, slowly, on paths that are genuinely uncertain over long timescales. A nudge sends them outward into interstellar space. A nudge in the other direction sends them falling inward for millions of years. Their membership in the solar system is contingent. They belong to the Sun right up until they don't, and the transition from belonging to not belonging happens gradually, continuously, across a vast zone of loosely held objects. This is not a line, it is a gradient. Think of it less like the edge of a country and more like the edge of an atmosphere. Earth's atmosphere does not end at a specific altitude. It thins. The density drops. At 100 kilometers, you define something called the Kármán line for aeronautical purposes, but molecules of air still exist above that. At 500 kilometers, there are still enough particles to create measurable drag on spacecraft. At 10,000 kilometers, the exosphere bleeds almost imperceptibly into the solar wind. There is no moment where atmosphere becomes not atmosphere. There is a zone of transition. The solar system has the same structure on a scale that spans hundreds of thousands of AU. The Sun's influence fades. The galaxy's influence rises. Somewhere in that gradient, the math tips from one to the other, but the objects in that gradient zone feel both. What makes this strange is that we are talking about our own solar system, the thing we live inside, and we cannot draw a simple line around it. The boundary of our local domain is genuinely ambiguous. That is not a failure of knowledge. It reflects something real about how gravity works and how structures dissolve at their edges. The solar system is not a closed container with a wall. It is a gravitational well sunk into the fabric of the galaxy, and the galaxy fills in around it at the margins. The outermost Oort Cloud objects are both inside the solar system and subject to forces that could remove them from it at any moment. They are in a permanent borderland. Every long-period comet that eventually falls inward came from that borderland, nudged loose from its marginal orbit by something, a passing star, a galactic ripple, a perturbation that accumulated over millions of years until the orbit stopped closing and the object began its long fall toward the Sun. Wherever you draw the boundary, the honest answer is the same. The solar system is bigger and stranger and less well defined than any textbook diagram has ever suggested. For something containing trillions of objects, the Oort Cloud has given astronomers almost nothing to look at directly. No telescope has ever resolved an individual object sitting out there in its proper orbit. No spacecraft has passed through it. Every number we have, the size estimates, the population counts, the composition guesses, comes from inference, from reasoning backward through the comets that fall inward and the physics that governs how they move. That is an extraordinary situation. We are describing one of the largest structures in the solar system without having seen any of it. And when you cannot see something, you cannot know what you are missing. So the real question is not just what is out there. The question is, what might be out there that we have not accounted for at all? Start with Planet 9. This is the most discussed possibility in outer solar system research over the last decade. It begins with a pattern in the data that nobody fully expected. A group of extreme trans-Neptunian objects, small worlds with orbits stretching far beyond the Kuiper belt, are not distributed randomly. Their orbital paths cluster together in a way that statistics say should not happen by chance. The probability that this clustering is random noise is low enough that many astronomers take it seriously as a signal. Something is herding these objects. Something massive enough to gravitationally shepherd a population of distant bodies into aligned orbits over billions of years. The leading hypothesis is an undiscovered planet, somewhere between 5 and 10 times the mass of Earth, sitting in a wide, eccentric orbit that keeps it far from the Sun for most of its journey. Some of the proposed orbits for Planet 9 would place it hundreds to thousands of AU from the Sun at its farthest point, well inside the inner Oort Cloud region. It would not be a gas giant. It would be something more like a super-Earth, dark, cold, reflecting almost no sunlight. If it exists, we may have already imaged it in archival sky surveys without recognizing what we were looking at. The search is ongoing. Nothing has been confirmed. But a planet is not the only large thing that might be hiding out there. The Oort Cloud almost certainly contains objects far bigger than the few kilometer icy bodies that eventually become comets. Dwarf planet-scale objects, bodies hundreds of kilometers across, potentially comparable to Pluto or Eris in size, could be distributed through the cloud in numbers no one has properly estimated. The challenge is simple. Objects that far from the Sun reflect almost no light. A body 500 kilometers wide sitting at 10.000 AU would be so faint that no current telescope could detect it in a reasonable survey. We have found Sedna at 76 AU at its closest approach. Sedna pushed the limits of what was observable at the time of its discovery in 2003. The true Oort Cloud sits 30 to 40 times further than that. Whatever population of large bodies exists, there is invisible to us with current technology. The count of dwarf planet-scale objects in the Oort Cloud is essentially unknown because we have never had the means to look. Then there is a possibility that cuts even deeper. The Oort Cloud can lose objects to interstellar space. Galactic tides strip the outermost bodies away continuously. A passing star can eject a significant number of objects entirely in a single close encounter. This process runs in both directions. During the Sun's early history, when it was still embedded in the stellar cluster where it formed, sibling stars were close enough that gravitational exchanges could have transferred material between protoplanetary disks. Objects that condensed around a neighboring star could have been captured into wide, loosely bound orbits around the Sun during those early close passages. The outer Oort Cloud, where the Sun's gravity holds objects barely at all, is precisely the region where captured interstellar material would settle. Some fraction of what we call Oort Cloud objects may have formed around a completely different star, condensed from a completely different protoplanetary disk, then pulled into our solar system billions of years ago during an encounter that is now ancient history. When a long-period comet eventually falls inward from the very outer cloud, its surface chemistry might carry the signature of a foreign stellar environment. We would have no way of knowing. Beyond that, the population of Oort Cloud objects is almost certainly more structurally complex than a simple collection of individual icy bodies. Binary objects, two bodies orbiting each other as a paired system, are known to exist in the Kuiper belt at significant rates. There is no reason to assume the Oort Cloud is different. Objects with small companion moons, loosely bound pairs drifting through the cloud together, groups of fragments from ancient collisions still traveling on nearly identical orbits. All of these structures are plausible, consistent with what we know about small body populations elsewhere. Completely unobserved in the Oort Cloud itself, the cloud is large enough and sparse enough that collisions between objects are extraordinarily rare. Once a binary pair forms, or a fragmentary cluster disperses into a shared orbital path, there is little to disrupt it over billions of years. These structures could persist in the outer cloud in essentially pristine form from the early solar system. We would have no knowledge of them. What makes all of this genuinely unsettling is the scale of the uncertainty. The Oort Cloud is not a remote curiosity at the edge of someone else's solar system. It surrounds us. It is part of our solar system, and it is one of the least observed, least understood, most poorly characterized regions in all of solar astronomy. We have mapped the surfaces of planets hundreds of millions of miles away in fine detail. We have tracked individual asteroids to within meters of their predicted positions. And the vast shell that wraps the entire solar system in a sphere extending to 100,000 AU remains effectively invisible, populated by objects we have never counted, structured in ways we have not verified, possibly harboring bodies whose existence we have not yet imagined. What else is out there in the dark beyond 10,000 AU? In orbits that have never been mapped and around objects that have never been seen is a genuinely open question. Voyager 1 launched in September of 1977, and by any measure that matters to a human being, it has travelled an extraordinary distance. It has crossed the orbit of every planet in the solar system. It has passed through the heliopause, the boundary where the sun's wind finally gives out against the pressure of interstellar space. It is, right now, more than 130 astronomical units from the sun. That is more than 130 times the distance from the Earth to the sun, or roughly 12 billion miles of empty space between that small metal craft and the star that launched it. No human-made object has ever been farther. By any reasonable definition of the word, Voyager 1 is the most distant thing we have ever sent anywhere, and it has not come close to leaving the solar system. This is the number that stops most people cold when they first hear it. Voyager 1 has been travelling for nearly 50 years. It moves at roughly 38,000 miles per hour relative to the Sun. At that speed, it will not reach the inner edge of the Oort Cloud for approximately 300 years. 3 centuries of continuous travel just to arrive at the beginning. Once it gets there, crossing the full depth of the cloud will take another 30,000 years. By the time Voyager 1 exits the far side of the Oort Cloud, its nuclear power source will have been dead for almost 30,000 years. The spacecraft will be cold and silent and completely unreachable, drifting through the outer cloud with no way to tell us what it sees. This is not a rounding error. This is what the solar system actually looks like when you account for all of it. It helps to put the 300-year figure into human terms. 300 years ago was the early 1700s. The steam engine had not been invented yet. The United States did not exist as a country. Isaac Newton had just recently published his laws of motion, and most of the world still travelled on horseback. The entire span of the Industrial Revolution, every war of the modern era, the invention of electricity and flight and satellites and computers, all of that human history fits inside the time Voyager 1 still needs just to reach the beginning of the Oort Cloud. The gap between where Voyager is now and where the cloud begins is not measured in decades. It is measured in centuries of sustained flight at speeds no human has ever directly experienced. What makes this harder to absorb is how fast Voyager actually is. 38,000 miles per hour is not slow. A commercial aircraft flies at roughly 575 miles per hour. Voyager moves at about 66 times that speed. If you could drive a car at Voyager's velocity, you would circle the Earth more than once every minute. It crossed the distance from Earth to the Moon in roughly 6 hours. It passed Jupiter in less than 2 years. By any standard built around human experience, this spacecraft is extraordinarily fast, and it still needs 300 years to reach the inner edge of a structure that is part of our own solar system. The reason is scale. The Oort Cloud does not begin until around 2,000 astronomical units from the Sun. Voyager is at 130. The remaining distance is not small. If you laid the entire journey Voyager has already completed end to end, you would need to repeat it more than 14 times just to reach the cloud's inner boundary. Everything Voyager has done in nearly 50 years of flight is a small fraction of what remains. The planets, the heliosphere, the interstellar medium Voyager is now crossing, all of that together is still just the innermost portion of the Sun's gravitational domain. No propulsion technology currently in existence changes this in any meaningful way. The fastest spacecraft ever launched, the Parker Solar Probe, reached speeds above 430,000 miles per hour during its close solar approaches. That is genuinely remarkable. At that speed, the journey to the inner Oort Cloud would still take decades. Getting through the full extent of the cloud would take thousands of years. There is no engine humans have built, and no engine currently on a drawing board that would deliver a spacecraft to the Oort Cloud within a single human lifetime. The physics required are beyond anything we have yet achieved, and the gap between what we have and what we would need is not a small one. This creates a strange situation. The Oort Cloud is our solar system. It is the outer shell of the structure the Sun gravitationally owns. It formed from the same material that built every planet and moon we have ever studied. Comets falling from it have been visible to humans throughout all of recorded history. In one sense, the Oort Cloud is intimately connected to us, the origin point of some of the most spectacular objects ever seen in the night sky. In another sense, it is completely and perhaps permanently beyond our reach. We live inside something we cannot visit. We are surrounded by a structure we have never directly observed and may never observe within any timescale that feels real. This is what separates the Oort Cloud from every other frontier in solar system exploration. Mars is far, but spacecraft reach it in months. The outer planets are distant, but Voyager passed them within years of launch. Even the Kuiper Belt, which once seemed impossibly remote, was visited when New Horizons flew through Pluto's neighborhood in 2015. The Oort Cloud is different. It is not the next step in a sequence of increasingly ambitious missions. It is a destination that falls entirely outside the range of anything we know how to build. The technology required does not yet exist, and the timeline for developing it is not clear. Every piece of hardware humans have ever launched is still, in cosmological terms, essentially next door to the Sun. Even the fastest object humanity has ever sent into space will not arrive at the Oort Cloud within the lifetime of anyone who built it, or their grandchildren, or any generation that can be concretely imagined. In October of 2017, astronomers detected something moving through the inner solar system that did not belong to it. The object was picked up by the Pan-STARRS telescope in Hawaii. and at first it looked like a comet or an asteroid on an unusual path. Then the orbital math came back. The trajectory was hyperbolic, not slightly hyperbolic, dramatically, unmistakably hyperbolic. Whatever this object was, it had not come from the solar system. It had come from somewhere else entirely, fallen into the sun's gravitational reach, swung around it, and was now heading back out again at a speed nothing bound to our sun could achieve. Astronomers named it Oumuamua, a Hawaiian word meaning something like a messenger from afar arriving first. The name fit better than anyone fully appreciated at the time. Oumuamua was strange in almost every measurable way. It was elongated, possibly cigar-shaped or flat like a disc, depending on which model you trusted. It showed unexpected acceleration as it moved away from the sun, more than could be explained by gravity alone. It had no visible coma, no tail, none of the outgassing behavior you would expect from a comet. Explanations multiplied fast. Outgassing of hydrogen, a fragment of a shredded planetesimal from another star. Something nobody wanted to say out loud, but several serious researchers eventually wrote up in peer-reviewed journals. Whatever it was the first confirmed visitor from another stellar system, and it passed through too quickly for any spacecraft to reach it. It was gone before the scientific community had fully registered what it was looking at. Then, in 2019, came something clearer. Comet Borisov was discovered by an amateur astronomer named Gennady Borisov, and its orbit left no room for argument. The trajectory was hyperbolic, the excess velocity was large, and unlike Oumuamua, it looked like a comet. It had a coma. It had a tail. Spectroscopic analysis of the material boiling off its surface showed water ice, carbon monoxide, a composition not dramatically different from comets born in our own solar system. Borisov had formed around another star, travelled across interstellar space, and arrived here carrying chemistry that looked remarkably familiar. 2 confirmed interstellar objects in 2 years, after centuries of watching the sky and finding none. Either the solar system had hit a strange streak of luck, or interstellar objects passed through far more often than anyone had assumed, and we had simply not been watching carefully enough to catch them before. The second explanation is almost certainly correct. Models built after these detections suggested that interstellar objects the size of Oumuamua should pass through the inner solar system roughly once a year. Most go undetected because they move fast, they are small, and the window to spot them is narrow. The upcoming Vera Rubin Observatory, with its ability to survey the entire accessible sky every few nights, is expected to catch several of them. The detections in 2017 and 2019 were not anomalies. They were the first glimpses of something that had always been happening. This is where the Oort Cloud becomes directly relevant. If interstellar objects pass through the solar system with reasonable frequency, and if the sun's gravity can tug on them as they pass, some fraction of them can be captured. Not many. The geometry and the speeds involved make capture difficult. But the solar system has been around for 4.5 billion years, and even a rare event repeated across that much time adds up. During the sun's earliest period, when it was still embedded in its birth cluster surrounded by hundreds of sibling stars, the stellar separations were far smaller than they are today. Objects loosely held by one star were within reach of another. Protoplanetary disks overlapped in gravitational influence. The exchange of material between young stellar systems was not just possible, it was likely. The outer Oort cloud is precisely where captured material would end up. Objects moving in from interstellar space carry more velocity than objects native to the solar system. To be captured, they need to lose enough energy to become bound, and that is most likely to happen at the outermost edge of the Sun's gravitational domain, where the Sun's pull is weakest, and where a slight nudge from a passing body or the galactic tide might be just enough to tip a fast-moving interloper into a loosely bound orbit. The inner solar system cannot capture these objects easily. The outer Oort cloud can, or could at least, when the Sun was young and the stellar neighborhood was crowded. What this means is unsettling in a quiet way. When you look at a long-period comet falling inward from the very outer cloud, you are probably looking at something that formed in our own solar system 4.5 billion years ago, but probably is doing a lot of work in that sentence. Some fraction of those inbound objects may have formed around a different star entirely. Their ice carries the chemical signature of a different protoplanetary disk, a different stellar neighborhood, a different history. We do not yet have the tools to tell the difference reliably. The spectroscopy required to distinguish an Oort cloud native from an interstellar capture is at the edge of what current technology can do, and long-period comets move fast and spend only a short time close enough to study in detail. The boundary between the solar system and interstellar space has always been treated as a clean line. Interstellar space on one side, our solar system on the other. What the Oort cloud suggests, and what Oumuamua and Borisov made concrete, is that the line was never clean. Objects cross it. They have always crossed it. The Sun has been exhaling comets into interstellar space for billions of years, and interstellar space has been sending material back. If material can cross between star systems, then some fraction of what we call the Oort cloud may have never originated around our Sun at all. The Oort cloud is not a permanent fixture. It is eroding right now, has been eroding since the day it formed, and will continue eroding until there is nothing left to erode. The process is slow by human standards. It is not slow by any other standard that matters. Start with the losses that are already happening. Every time galactic tides nudge an outer cloud object into an unstable orbit, that object either falls inward toward the Sun or drifts outward past the point where the Sun's gravity can hold it. Either way, it does not come back. Every passing star that perturbs a cluster of outer cloud objects ejects some fraction of them into interstellar space permanently. They become the galaxy's objects now, no longer the Sun's, and every comet that falls all the way inward into the heat and gravity of the inner solar system eventually meets one of a few endings. It gets shattered by tidal forces. It gets absorbed into a planet's atmosphere. It sublimes away, orbit by orbit, each pass around the Sun boiling off more of its ice until there is nothing left but a scattered trail of debris. Whatever it was, it is gone from the reservoir forever. These individual losses are small, one object here, a handful there. But the cloud contains perhaps 1 trillion objects, and it has been losing them for 4.6 billion years. Models that track this erosion suggest the Oort cloud today may hold only a fraction of what it originally contained when the solar system first settled into its current configuration. Some estimates put the losses as high as 90% of the original population. The cloud you would have seen 4 billion years ago was vastly denser, vastly more populated. What exists now is already the depleted version. It is still enormous by any human measure, but it is a smaller thing than it was. The pace of loss is not constant. When a star passes close, the ejection rate spikes. The approach of Gliese 710, roughly 1.3 million years from now, will send a wave of perturbations through the outer cloud, unlike anything in recent solar history. Some fraction of the objects disturbed during that encounter will be lost outright. Others will be sent inward as a comet shower, a period of elevated comet flux in the inner solar system that could last hundreds of thousands of years. After the encounter passes, the loss rate drops back down. Then another star approaches. Then another molecular cloud crosses a close enough path. The erosion is punctuated, uneven, driven by events the Oort Cloud has no defense against. Now look further forward. Not millions of years, but billions. In roughly 5 billion years, the Sun will exhaust the hydrogen fuel at its core. The fusion that has powered it since before the Earth existed will falter. The core will contract, and the outer layers will do what outer layers of dying stars do. They will expand. The Sun will swell into a red giant, growing to a size that will swallow Mercury and Venus, and possibly Earth itself. This is the same process that made Betelgeuse the enormous, bloated thing it is today. Our Sun will go through a version of the same transformation. When that happens, the Sun will not just expand, it will also shed mass. Red giants lose enormous quantities of material through stellar winds, bleeding their outer layers into space over millions of years. For the Oort Cloud, this matters enormously. The strength of the Sun's gravitational grip depends on its mass. As the Sun sheds mass, that grip weakens. Objects that were marginally stable at 80,000 or 100,000 AU become unstable. Their orbits widen, slow, and eventually detach entirely. The outer cloud does not collapse inward during this process. It disperses outward, objects drifting away from a Sun that can no longer hold them, becoming part of the general field of interstellar debris. The inner cloud, denser and more tightly bound, will fare somewhat better for a while. But the Sun's red giant phase also means a much larger, much hotter stellar surface, radiating energy outward. Objects that have been frozen for billions of years, preserved intact since the early solar system, will begin to experience warmth they have never felt. Some of the innermost Oort Cloud objects may be vaporized or significantly altered as the habitable zone sweeps outward past orbits it was never close to before. After the red giant phase, the Sun will shed its outer layers entirely in a brief, brilliant burst called a planetary nebula. What remains is the core, a white dwarf, dense, small and dim. It will contain perhaps half or slightly more of the Sun's current mass. The gravitational field reorganizes around this smaller, dimmer remnant. Whatever Oort Cloud objects survive the red giant phase and are still loosely orbiting this remnant will find themselves in altered circumstances. Some will eventually drift away over further billions of years. Some may persist in highly eccentric orbits around a cold white dwarf for an almost incomprehensible span of time. But the cloud as a functioning, self-replenishing system will be gone. There will be no mechanism to replace what has been lost. No new objects forming in a protoplanetary disk. No ongoing process of ejection from a living planetary system. What is left in the very far future is a cold stellar remnant surrounded by dispersed debris. Not a cloud, not a reservoir, just the last scattered objects on their slow, solitary orbits. Long after the last comet has fallen inward and the last scattered object has drifted away, the outer edge of the solar system will be gone. and there will be nothing left to mark where it was. There is a version of the solar system that most people carry around in their heads, and it is almost entirely wrong in one specific way. Not wrong about the names of the planets, not wrong about the order they appear in, or the rough fact that they orbit a star. Wrong about scale. Wrong in a way that is so fundamental it changes what the solar system actually is. Every diagram ever printed in a school textbook, every animation that shows the planets spinning around the sun, every poster hanging in a classroom, they all commit the same distortion. They have to. If you drew the solar system to true scale, the planets would be invisible. You would need a sheet of paper the size of a city block just to fit Neptune at a readable size, and even then Earth would be a speck too small to see without magnification. Here is a version of that scale you can hold in your mind. Imagine the sun reduced to a single printed period, the kind at the end of a sentence on this page. At that scale, Earth's orbit around the Sun is a circle with a diameter of roughly 1 millimeter. Neptune sits about 3 centimeters out. The Kuiper Belt, the region that includes Pluto and thousands of other icy bodies, ends at maybe 6 or 7 centimeters from that period. Everything, every planet, every moon, every asteroid belt, the entire region of the solar system that humans have explored with spacecraft, all of it fits inside a circle smaller than a grain of sand in that model. And the outer Oort Cloud? At that same scale, the outer Oort Cloud forms a sphere roughly 40 feet across. The period sits at the center of a room, and the edge of the solar system is somewhere outside the building. That is not a poetic exaggeration. That is the actual geometry. The planets are not the solar system. They are a tiny warm core at the center of something almost incomprehensibly larger, a gravitational domain that stretches outward for 100,000 AU in every direction. Everything inside that domain, every object still orbiting the Sun rather than the galaxy, is part of this solar system. Most of it has never been mapped. Most of it has never been seen. What does this mean for the search for life elsewhere? It changes the framing entirely. When people talk about searching for life in other star systems, the assumption is usually that we are well inside our own, and they are somewhere out there across a vast and empty gulf. But the nearest star system, Alpha Centauri, is about 4.2 light-years away. The outer Oort Cloud extends to somewhere around 1.5 light-years from the Sun. That means, at its true outer edge, our solar system reaches roughly a third of the way to the nearest star. Alpha Centauri almost certainly has its own equivalent of an Oort Cloud, its own shell of distant icy debris extending outward from its gravitational center. It is not impossible that the outermost edges of these two systems are closer to each other than the outer Oort Cloud is to the Sun's own planets. The boundary between our solar system and interstellar space is not a clean wall. It is a zone where the Sun's gravitational grip fades slowly into the competing pulls of the galaxy and its neighboring stars. This has consequences for how we think about interstellar travel. The popular image is a spacecraft leaving Earth, passing the outer planets, and then crossing a kind of threshold into the void between stars. But there is no threshold. There is the heliosphere, where the solar wind stops, which Voyager 1 crossed around 120 AU, and then there is the gravitational edge of the solar system, which is not at 120 AU but somewhere around 100,000 AU. A spacecraft that crossed the heliopause and entered interstellar space in the physical sense is still, gravitationally, inside the solar system. It is still moving through territory that belongs to the Sun. A spacecraft would have to travel 1,000 times further than Voyager has gone to reach the gravitational boundary of our own solar system. Interstellar travel does not begin at the edge of the planets. It begins at the edge of the Oort Cloud, and that edge is a light year and a half away. The scale also reshapes what it means to be a small rocky planet orbiting a medium-sized star. We tend to think of Earth as sitting inside the solar system. In one sense, that is true. In another sense, Earth is pressed right up against the Sun, huddled in the innermost fraction of a percent of the Sun's domain, so close to the central star that the vast majority of the solar system lies beyond us in all directions. The cold, dark outer reaches of the cloud are far more representative of what the solar system actually is than the bright inner zone where the planets orbit. The planets are the exception. The cold and dark are the rule. This is the thing that no textbook diagram has ever conveyed. The solar system is not a warm-lit region with a dark void beginning somewhere past Neptune. It is an enormous sphere of gravitationally bound objects, most of them frozen, most of them dark, most of them silent, extending outward from the Sun for a distance that approaches the space between stars. The sunlit planetary zone is a small interior room. The Oort Cloud is everything else, and everything else is most of it. The full extent of what the Sun holds, the complete size of our local domain, is larger than any illustration has ever managed to show. We started with the assumption that the solar system ends somewhere near Pluto. That assumption is built into every diagram, every classroom poster, every animation that shows 8 planets circling a central star and then just stops. The image is clean and confident and almost entirely misleading. What the Oort Cloud reveals is not just a larger solar system, it reveals how narrow our picture of it has always been. Think about what humanity has actually managed to do in space. We have telescopes positioned beyond Earth's atmosphere that can resolve the light of galaxies 12 billion light-years away. We have landed instruments on the surface of a comet. We have mapped the faint temperature variations in the cosmic microwave background, the oldest light in the universe, radiation from roughly 380,000 years after the Big Bang. We have sent spacecraft out of the planetary system entirely. Voyager 1 is crossing interstellar space right now, past the heliopause, in the region between stars. By almost any measure, human astronomy has reached things so far away they are nearly incomprehensible. And yet, the outer Oort Cloud sits roughly 1 to 1.5 light-years away. Not billions, not millions, 1 to 1.5, a fraction of the distance to the nearest star. The closest truly deep astronomical unknown in existence, and we have never directly seen a single object in it. Not one. Every estimate of how many objects are out there, every map of its 2 regions, every calculation of its total mass is built on inference. We are reading the cloud from its debris, the comets it sends inward, the orbital signatures they carry. We have never looked at the source. The Oort Cloud is right here, surrounding the solar system on all sides, and it remains completely invisible to us. This is the strange situation astronomy finds itself in. The universe at large is in many ways better observed than our own backyard. That is not a figure of speech. The Hubble Space Telescope spent 1,000,000 seconds staring at a patch of sky the apparent size of a grain of sand held at arm's length and found 10,000 galaxies in it. We have chemical profiles of stars hundreds of light-years away. We have detected planets orbiting other suns using the faint dimming of starlight. All of that, and the reservoir enclosing our own solar system, remains a theoretical object, named after a man who deduced it from 19 comet orbits, never photographed, never resolved, just inferred. What makes this genuinely unsettling is the scale problem. The Oort Cloud is not difficult to observe because it is far away in the way that distant galaxies are far away. It is difficult to observe because its objects are small, dark, cold, and spread across an almost inconceivably large volume of space. The average separation between neighboring Oort Cloud objects is tens of millions of kilometers. Even if you aimed every telescope on Earth at the right patch of sky, you would likely see nothing. The cloud does not glow. It does not emit. It sits in frozen silence at temperatures only a few degrees above absolute zero, waiting. There is no signal. There is no edge that lights up. There is just the dark. Every comet that has ever crossed the night sky was a piece of that dark falling inward. Ancient observers in China, in Babylon, in Egypt, watched bright comets appear without warning and recorded them as omens, as signs of disaster or of divine attention. They were not wrong that something significant was happening. They just did not know what. What they were watching was a fragment of original solar system material, ice and dust preserved unchanged for 4.5 billion years, making its first journey toward the sun since the planets formed. Some of those comets had never been close to the sun before. Their surfaces had never been heated. Their ice had never sublimated. And then a passing star or a ripple in the galactic tide nudged their orbit just slightly, and they began the long fall inward, taking millions of years to arrive, and finally appearing in the inner solar system as a bright smear of light that lasted a few weeks before disappearing back into darkness. The cloud is still out there, right now, in every direction, trillions of objects in slow, wide orbits that take hundreds of thousands of years to complete. Most of them will never fall inward. Most will drift in their distant loops until the sun swells and dies and the cloud disperses. But some of them are already falling. Somewhere in the outer cloud right now, an orbit is being disturbed. An object that has been in the same slow path for 4 billion years is beginning a new trajectory, one that will eventually carry it past Neptune, past Jupiter, past the asteroid belt, into the inner solar system where the sun's heat will boil its surface and build a tail stretching millions of kilometers behind it. That process has probably already begun for comets we will see centuries from now. The solar system ends somewhere out in the dark, more than a light year from the sun, and every time a comet falls inward out of that dark and crosses the sky above us, it is sending a fragment of that answer our way.